Good evening, everyone. Am I audible?
Yes, sir.
Okay, fine. Let's wait for 4 minutes. Is my screen visible to all?
Yes, sir.
Okay. Good evening, everyone. So I hope you have gone through all the lectures in week three. So week three of this course on fluid mechanics was basically dedicated to a very important concept of Reynolds transport theorem. So can anyone share his or her views on Reynolds transport theorem? Why do you think this theorem is so important, Reynolds transport theorem? Anyone? Why Reynolds transport theorem is so important? Okay, the reason is very simple. Whenever you study mechanics, it can be solid mechanics, it may be fluid mechanics, it may be any other mechanics, okay, it may be soil mechanics. The most important thing is that whenever you solve a problem in mechanics conceptually, you basically try to understand and you basically model the conservation equations. So what are these conservation equations? Conservation of mass, conservation of linear momentum, conservation of angular momentum, and conservation of energy. Now, this Reynolds transport theorem is basically uh, a theorem which gives you a mathematical form, an equation, by which you can derive all these conservation equations. So it is basically a single equation by which you can derive all these equations simply by choosing appropriate intensive and extensive properties. Okay, and more importantly, it is basically a theorem which uh, the relates the physical mechanisms that is going on inside a system with that of a control volume. A system and a control volume are not the same thing. Okay, so can you tell me what is the difference between a system and a control volume? Anyone?
System represents particle set of particle, but
Yeah.
control volume represent a space. set of
Yes,
space.
space. So it is basically we have seen that whenever you study fluids, you must have seen, or if you don't know, then there are two approaches by which you can study uh, any mechanics. One is the Eulerian approach, and second one is the Lagrangian approach. So the system is basically related to the Lagrangian approach, and the control volume is related to the Eulerian approach. Now, the most important property of a system is that its mass is conserved. Mass remains fixed. Okay. However, in case of a control volume, mass inflow through the control surface and mass outflow means there is influx and efflux of masses can take place. Okay. So that is the thing. However, for studying fluid mechanics or any mechanics, we need a relationship between these system variables and the control volume variables. So that is given by Reynolds transport theorem. So I once again uh, suggest all of you that if you have any confusions related to Reynolds transport theorem, please study, go through the lectures once again. Please follow the reference books, okay? Because Reynolds transport theorem is not simply about solving problems. It is the most fundamental concept in fluid mechanics, okay? And you should have a very good grasp over Reynolds transport theorem. You can derive the continuity equation, you can derive the momentum equation, you can derive the energy equation from this single Reynolds transport theorem. So, to begin with today's session, initially I have included a problem which is basically in the form of a multiple choice question. Okay, so you can see that the question tells that there is a flow field, okay, which satisfy the divergence of velocity is zero as the continuity equation. Okay, so there is a flow field represented by a velocity field v such that the divergence of the velocity is zero satisfies the continuity equation, that is the conservation of mass. Now, if divergence of velocity is equal to 0, then it always represents A, steady and uniform flow, B, unsteady and non-uniform flow, steady and incompressible flow, unsteady and incompressible flow, and E is incompressible flow. So, please tell me which one will be the correct option. Please read the question very carefully. A flow field satisfying del dot V equal to 0 as the continuity equation represents always a steady and uniform flow, unsteady and non-uniform flow, steady and incompressible flow, unsteady and incompressible flow, and the last option is incompressible. Anyone? What will be the answer? Correct option? If you are not sure, at least you can try.
Option C, steady and incompressible, maybe.
Okay, so I got one response. Option C, steady and incompressible flow. Okay. Anyone else?
I think it's option A, steady and uniform flow.
Steady and uniform flow. Okay, so till now I got option A, option C. Okay. Anyone else? Now let me tell you, this question is a very simple problem, but there is a little twist in this question, and you can always expect this type of MCQs in competitive exams. Okay. But of course, it is a very simple problem. Now, uh, the full form of the continuity equation is del rho del t. Okay. In terms of Cartesian coordinate, I am telling del rho u del x plus del rho v del y plus del rho w del z is equal to 0. So this is the continuity equation for a fluid. Okay. Now, first option is steady and uniform. Okay. In the equation, it is given that divergence of velocity is equal to 0 is the continuity equation. It means that the condition that is valid in this case is del u del x plus del v del y plus del w del z is equal to 0. Okay. So if suppose someone told option A, if it is steady, then I can understand that this particular del rho by del t will vanish, fine. But if it is uniform, then do you think that del u del x del v del y del w del z, all these things will be there? Definitely all these things will be 0, then also it will be 0. So that is one option I have understood. Okay. Then someone told that it is option C, steady and incompressible. Okay. Now if it is steady and incompressible, in case of steady flow, again this del rho by del t will vanish. Since density is constant, incompressible flow, so the rho will come out and finally you will be left with this. Okay. So that is also a possible option. But please look at the question carefully. It is given that a flow field satisfying del dot v equal to 0 as the continuity equation represents always. Okay. You have to choose an option which is always correct. Okay. Always. In any case. So now I am giving you a situation. Okay. If this is uniform flow, suppose let us come to option A. Okay. If it is steady and uniform, then this individual velocity gradients del u del x del v del w del w del z are equal to 0. Okay. Now when the flow is uniform, it means that with space it is not changing. Okay. So with space it is not changing means this will be 0, this will be 0, this will be 0, it is steady, this will be 0, everything is 0. Okay. But nothing has been mentioned. Okay. Secondly, if it is steady, okay, if it is steady, then this will vanish, and as someone told option C, then all the rows will come out, then del dot v will be 0, that we have understood. But as it is asked in the question that what is the condition when it is always 0, okay, so you have to select an option which is the most general option. And the most general option is, you can look at option E, incompressible flow. If the flow is incompressible, then also this will vanish. Okay, then also del rho by del t will vanish. Del rho by del t will vanish. Since it is incompressible, rho is constant, all these things will come out, and del dot v will be 0. Okay, del dot v will be 0. So the most general means it is basically like you have to select the superset. Okay, the most general option. So the answer is option E, that is incompressible flow. Okay, now let us move to the next problem. Consider a cube with 2-meter edges parallel to the coordinate axis located in the first quadrant with one corner at the origin. By making use of the velocity distribution 5x i cap, 5y j cap, 10z k cap, find out the flow through each phase and show that no mass is being accumulated within the cube if the fluid is of constant density. Okay. So let us draw a figure. So what is given in the first quadrant, there is a cube. Okay. In the first quadrant, there is a cube. The length of its edges are 2 meter. It is given in the question. The length of the edges are 2 meter. What else is given? Edges are parallel to the coordinate axis located in the first quadrant. It means that, and one more thing, with one corner at the origin. Okay. So say this is our origin. One corner is located at the origin. Okay. And the edges of the cube are parallel to the coordinate axis. Okay. So this is say our x-axis, this is say our y-axis, and say this is our z-axis. Okay. Now, if this is the case, what will be the coordinates of each of these points? Let us name these points. Okay. Say this is origin. Fine. Say this corner is A. This is B. This is O. This is C. This is D, E, F, and G. So I think all the yes. So we have named. So this corner is A, B, C. This is the origin O, D, E, F, G. Okay. So can you tell me? Now it is given in the question that it is a cube. So if it is a cube, means all the lengths of all the sides are same, and the value is given as 2 meter. So the coordinate of O, that is the origin, is definitely 0, sorry, it is 0, 0, and 0. Okay. Now, what is the coordinate of C? What will be the coordinate of C? Coordinate of point C?
0, 0, 2.
0, 0, 2.
0, 2, 0.
It will be 0, 2, 0. Good. Coordinate of point D?
2, 2, 0.
It will be 2, 2, 0. Coordinate of point 2? Sorry, point E?
2, 0, 0.
2, 0, 0. Fine. What will be the coordinate of point A?
0, 2, 2.
0, 2, 2.
0, 2, 2. Is this what you told? What is the coordinate of point
Yes.
A? 0, 2, 2. Okay, fine. What about point B?
0, 0, 2.
0, 0, 2. Fine. Coordinate of point F?
2, 0, 2.
2, 0, 2. And coordinate of point G?
2, 2, 2.
2, 2.
Yeah, it will be 2, 2, 2. Okay. So, this is clear, right? I hope this is clear. So, there is a cube such that one of the corner, now you can choose any corner as the origin, okay, according to your convenience. But the thing is, you have to decide the coordinates accordingly. Okay, you have to decide the coordinates accordingly. And all the coordinates are positive because it is given in the question that the cube lies within the first quadrant. Okay. Now a velocity distribution is given 5x I cap, 5y j cap, and minus 10z k cap. So from this, what can you make? We can very conveniently write that u, that is the component of velocity along the x direction, is 5x. Then what will be v? The component of velocity along y direction is 5y. And what will be w? The component of velocity along z direction is minus 10z. Okay. Minus 10z. Okay. Now what you have to find? You have to find out the flow through each phase. Okay. You find out the flow through each phase. So phase ABCO. Okay. Phase ABCO. What will be the flow through the phase ABCO? What is flow? Flow is basically
Area times
discharge.
velocity.
Discharge, yes, discharge. Area times velocity. Okay. So for phase ABCO, area is fixed for all the phases because it is a cube. What is the area for each of the phase?
4 square units.
Huh?
4 square units.
4, yeah, 4 meter square. 4 meter square
4
because
meter
it is
square.
given 2 meter edges, so it is 4 meter square. Okay, so area is fixed. So the only thing that you need to decide is what is the velocity. So what will be the velocity at this phase?
5x.
Yeah, 5x. But what will be the value of x for this? For this phase?
0.
0, right? 0. So for phase ABCO, it is 0. What will be the velocity for this phase? GFED. For phase GFED?
Sir, 5x. Here x is equal to 2.
Yeah, here x is equal to 2. So what will be the velocity? This
10.
velocity 10, and velocity multiplied with area. Area is 4. Right?
Yes, sir.
Yeah. So it will be
40.
40 meter cube per second. So this is the flow that is taking place along what? Along the x direction, right? Okay. Similarly, all of you please calculate and tell me what is the flow along the y direction, the total flow. See, so in the x direction, zero amount of fluid has entered or water has entered, okay, through phase ABCO, but 40 meter cube per second of fluid 40 meter cube of fluid has left this volume in 1 second of time. Okay, so this is for x-axis, along x-axis. Along y-axis, what is the value, you tell me? The net flow rate. Along y-axis means you consider this one, okay, BFEO. So through this phase BFEO, what will be the velocity along y direction? 5 times of y, but the value of y will be 0. And what is the velocity at this phase AGDC? So at phase AGDC, it will be 5 times into 2 because the y coordinate is 2 for this phase. Okay, so it will be 10 multiplied with 4. So 40. So along x also 40 meter cube per second, and along y also 40 meter cube per second. Is it clear?
Yes, sir.
Yeah. So similarly, what will be the net discharge along the z direction?
phase ACDE is equal to 0 or phase AGFB is equal to 40 meter cube per second.
For z direction, is it 40?
Yes, sir.
Look carefully. What is the velocity distribution for z direction? Minus 10z, right?
Oh, sorry, sir.
Yeah. So
80.
it will be just
80.
80.
80.
80. Yeah. But there is one little point that you have to keep in mind. See, this u, v and w, these are what? These are velocity components, right? And velocity is a vector. Now, this u and v, positive 5x, positive 5y. So, positive 5x we have considered, means this is a convention. You are always free to choose your own convention. But the convention while solving this problem till now, what we have chosen, positive 5x is along the positive x-axis. Positive 5y is along positive y-axis. But the z is negative, right? The w component, the z component is negative, minus 10z. It is given here, no? It is minus 10z. So, since it is negative, whichever phase you are considering, say this particular phase or this particular phase, okay? So, minus 10z means it is just in the opposite direction, right? Is
Yes,
it clear? Yeah. And
Yes, sir.
yeah, similarly, this is in the opposite direction. So basically, you can think of it like this, that 80 meter cube per second of water, 80 meter cube of water is entering this control volume in 1 second. And at the same time, 80 meter cube of water is getting removed from this volume in 1 second. Because why 80? Because these two positive 40s will make 80 along x and y direction, right? Is it clear? For x and y direction, 40 meter cube and 40 meter cube per second will make 80 meter cube per second, right?
Yes, sir.
But
Yes, sir.
these are outfluxes, means these, according to the convention that we have chosen, 80 meter cube per second of water is moving out of this volume through x-axis and y-axis. However, 80 meter cube per second of water is entering, if you're considering this as leaving, because it is minus 80 meter cube per second, is entering the volume in per second. So, what is the mass accumulated within this volume in 1 second?
Sir, 0. It will be null. 80 meter cube per second is entering and the same will be
Moving out.
outflux
Yeah.
to
Yeah. So, what is the mass accumulated? It is
0.
0. Yeah. So, that was the second part of the question. Show that no mass is being accumulated within the cube if the fluid is of constant density. Now, why this word is important? Why this last part is of constant density? Because the answer is very simple. If the density is not constant, okay, if the density is not constant, then what will happen? At each point the density will vary. Now for discharge we have directly used, means for when the density is constant, we know that A1 V1 is equal to A2 V2, right? And we have calculated the discharges or the flow at each phase using this only, area into velocity. But if the density is not constant, then the continuity equation becomes rho 1 A1 V1 is equal to rho 2 A2 V2, right? Or rho AB equal to constant. So the effect of density we have not considered anywhere. So inherently we have assumed that the density is constant. So I hope the problem is clear. And one important thing.
Yes, sir.
Yeah.
Sir, excuse me, sir.
Yeah.
Sir, can you please explain one more time how the 40 and the 8 year come at each side, please?
Okay, fine. I hope you have taken down the coordinates, right? Who was it who asked the doubt?
Sir,
Yeah,
it's
you
me,
have.
sir. Surya
Yeah, yeah.
Prakash.
Okay, so you have taken the coordinates, right?
Yes, sir.
Yeah. So I'll simply draw the cube. Okay, and this was our x-axis, this was our y-axis, and this was our z-axis. Now see, for x-axis, what we have considered when the velocity distribution was positive 5x. Okay, when the velocity distribution was positive 5x, so here it was 0, and through this phase 40 meter cube per second came out along x direction. This is clear, I hope.
Yes, sir.
Yeah. Now if you consider, now this was our origin. Yeah. If you consider about the y-axis, through this phase it was 0, and through this phase it was 40 meter cube per second. So y positive because our distribution was 5y. This is also clear?
Yes, sir.
Yeah. Now let's come to the z direction. So what was the z component of velocity? It was minus of 10z. So if we use minus of 10z, then through this phase, okay, through this phase, how much is entering or leaving? Whatever, it is 0. Okay, but through this phase, at this phase, whatever is the discharge, you forget the direction. What will be the discharge?
80, sir.
80, right? So the magnitude is 80. Okay, but what is the direction of this flow? It is minus 80. If you use this one, it was minus 10z, it is minus 80, right?
Yes, sir.
Yeah, so positive one, according to the convention that we have followed here, positive discharges are moving outside, right? We have considered the convention. See, you can follow your own convention, but the convention that we have followed while solving this problem, we have considered that since this was positive, it is moving outside. This was positive, it is moving outside. Since this is negative, so will it move outside or it will come inside?
It will come inside, sir.
Yeah, come inside. So in 1 second, 80 meter cube of water is entering this volume. However, if you add, since discharge is a scalar quantity, we can simply add it like a scalar. Okay. So 80 meter cube of water in 1 second, 80 meter cube of water is entering through the z direction. However, this 40 plus this 40, that is along x and y direction, 40 plus 40, 80, 80 meter cube of water is also leaving the volume in 1 second. So what is the net mass accumulated in 1 second? Hello?
Hello, sir.
Yeah, so is it clear now? See, 80
Uh,
meter cube has entered through this phase, right?
yes, sir.
But 40 meter cube along y has moved out and 40 meter cube along x has moved out. So
Yes, sir.
minus 80 plus 80. So what is the summation? Minus 80 plus 80 is
0, sir.
0. So in 1 second, no mass is accumulated in the cube. Is it clear now?
Clear, sir.
Yeah, okay.
Thank you, sir.
Yeah, thank you. Okay, so this kind of problems are very important. You will find many problems on this like this. Okay, so this is the solution, but as I have told you, means this is the answer, but you can choose your own convention. Anyways, let's move to the next problem. I hope you have gone through the concept of kinetic energy correction factor and momentum correction factor in the lectures. Was it covered in the lectures? Anyone? Please respond. Kinetic energy correction factor and momentum correction factor, was it there? Okay, if it was not there, then I'll skip this question. Let's move to the next problem. Okay. Now again, this problem is very interesting. Please read the question carefully. And there is a problem figure. A circular pipe 10 centimeter in diameter. Okay, so there is a pipe whose diameter is 10 centimeter. Has a 2-meter length which is porous. Now, it's a long pipe. Okay, but out of the total length, there is 2-meter length of the pipe which is porous. So, by porous, what do you mean here in a pipe? If a certain length of a pipe is porous, what will happen? What will happen if the certain length of a pipe is porous?
Certainly the water passes through
Yeah,
these phases.
yeah. So there will be leakage. So basically there will be leakage, right? So there is a pipe. This is the pipe whose diameter is 10 centimeter, and this is the 2-meter stretch where the pipe walls are porous. Okay. In this porous section, the velocity of exit, that is the leakage, is known to be constant. Means there is a constant emission of the fluid. Okay, whatever fluid is flowing through this pipe, in this porous section or porous length of 2 meter, there is a constant emission of this fluid through this porous length in the porous region. If the velocities at inlet and outlet of the porous section, means this is the inlet and this is the outlet. You can see that inlet V1, outlet V2. Okay. So the velocity at the inlet and the outlet of the porous section are how much? 2 meter per second at the inlet and 1.2 meter per second at the outlet. Okay. So V1 is 2 meter per second, V2 is 1.2 meter per second. You have to estimate the discharge emitted out through the walls of the porous pipe. Means you have to find how much water is being released, the flow rate through this porous pipe or the porous wall, and the average velocity, that is V. What is the average velocity of discharge through this porous stretch or porous line? So is the problem clear?
Yes, sir.
Yeah, problem is clear, right? So if the problem is clear, please take 3-4 minutes and try this problem, and let's see. Then we will discuss the solution. So basically it is the application of which conservation principle? So which conservation principle will you apply? Yeah,
Conservation of mass.
conservation of mass. Yes, good. So please apply conservation of mass and see. Okay. So you have to obtain two things, the discharge here and the average velocity of the water or the leaked water or the leaked fluid.
sir,
Yeah.
is the emitted average velocity is 0.01 meter per second?
Yeah, I'll just say, if please tell me what is the answer you obtained? Average velocity?
I just got 0.01 meter per second.
Okay, we'll see. We'll see the solution. Thank you.
Okay, sir.
Sir, velocity is 6.23 guna 10 to the power minus 3 meter per second.
Means velocity, average velocity.
Yes, sir.
Okay. And what is the discharge? The first part. There are two parts in this question. You have to estimate the discharge emitted out through the walls.
Discharge is equal to 3.93 guna 10 के power minus 3 meter cube per second.
Okay. Somebody wrote 0.063. Okay. Qmac equal to exit discharge. Fine. We'll see. Okay. So let's move to the solution part. Okay. So if A is the cross-sectional area of the pipe and the diameter of the pipe was 10 centimeter, so the cross-sectional area will be pi d square by 4. So it's basically 7.854 into 10 to the power minus 3 meter square. You please see what is important in these particular sessions is the means how to solve the problems. Okay, so there might be some errors in this calculation. So if it is there, so that's why I ask all of you to calculate once again. But please try to understand that try to understand the solution methodology, how it has to be done. Okay, so don't worry too much about the final answers. Okay, that can be that is not an issue here, but what is the procedure for solving the problem, that is important. So what I can suggest you is, when you discuss the solution, you please recheck the calculations. Okay, means whatever I am showing here, there might be some errors here in these calculations also. Okay, but you try to follow the procedure. So basically you have to the area you can find, the diameter of the pipe is given, so you can find pi d square by 4 is the area. Now, what is the discharge at the inlet? So inlet velocity is given, you multiplied with the diameter of the pipe, so you can find the inlet discharge. So basically V1 into A. So V1 was given as 2 meter per second. So V1 into A is the inlet discharge. And what is Q2? The outlet discharge, it is V2 into A. So the value of V2 was 1.2 meter per second. So V2 into A is the outlet discharge. Okay. Now the first part is, what is the discharge emitted through the walls? Now discharge emitted through the walls is basically whatever is the difference between the input and the output. That is, whatever is the discharge at the inlet and the outlet, if you find there is a difference. Okay, if there was no, now what is basically the continuity equation? Continuity equation tells us that if it is a incompressible fluid, that is area A1 V1 is equal to A2 V2. Okay, or more generally A into V, okay, is equal to some constant C. Okay, now here you can see that the discharge Q1 and Q2 are not same. Okay, now let me ask you one question. This particular condition A1 V1 equal to A2 V2 is coming from the conservation of mass, and we know that what is the original statement of the conservation of mass? Mass is neither created nor it can be destroyed, and it is always conserved. So in this problem, don't you think the conservation of mass has been violated? What is your view? Anyone?
Sir, excuse me, sir.
Yeah.
Sir, they said it was a porous type. So some liquid might be stored in that porous layer.
Okay. 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 Means some liquid might be stored in the porous layer. Means initially, means from time t equal to 0. That you are trying to tell? See, the idea is very simple. These two should be equal. Okay, means the idea is mass at one section should be equal to the mass at other section. Okay, the conservation of mass is not at all violated. Why not at all violated? What is the original statement? Original statement is mass should always be conserved, and mass is definitely conserved because Q1 and Q2 are not same, but whatever difference is there, that is the discharge that has the fluid that has moved out of this pipe through this porous zone.
The force.
Hello?
Yes, sir.
Yeah. Okay. So mass is conserved. Anyways, so the difference between Q1 and Q2. Okay. The difference between Q1 and Q2, Q1 that is whatever discharge is entering through the inlet is higher than the discharge through the outlet. So whatever in between the fluid that is lost, it has been emitted. So that is the discharge emitted. The difference between these two is the first part. The answer to the first part, it is the discharge emitted through the walls of the porous pipe. Now, the second part, surface. The second part asks you to calculate the average velocity. Now for average velocity, what you need, you have already the discharge with you. So you have already the discharge with you. So in order to find the velocity, average velocity, what you need the area. Okay, you need the area. So what is the area of emission? What is the area of emission?
Area.
Yeah. Huh?
Whose area passes through the
Yeah.
porous.
So what will be the value? Say this is the porous zone, right? This is the porous zone. This is the porous zone of the pipe. So what is the area?
Pi dh.
Pi d h.
L.
Fine. Or L, whatever. Yeah, fine. So is it clear why this is pi d L or pi d h, everyone?
Sir, but this doesn't mean that we have no obstruction
Huh?
for the leakage
Pardon?
of the fluid.
Yeah, please repeat.
I'm saying that if we
There is a lot of
send
disturbance in
the
your
pipe
side.
into it,
Hello? Can you please write in the chat box? Anyways, so it will be, see, the length of this porous zone was 2 meter. If I'm not wrong, yes. Yes, it was 2 meter. Now, the water which is getting leaked is through the surface area of this much length of the pipe. So if you cut this pipe, it will be basically a rectangle.
Hello, sir.
Yeah. Hello.
Sir,
Yes.
I was saying that in this particular case, the the fluid will be exiting from the pores only. So there shouldn't be some amount of factor of the total curved surface area.
Yeah.
But
See.
instead, we are considering the whole.
What you are telling is very much correct. Okay. What you are telling is very much correct. But in the question, it is written that the section of the velocity of exit is known to be constant. Okay. So when this particular thing is given to you, now if you look at the porous media flow, the governing equation or the governing law is the Darcy's law, right? So in Darcy's law, what does Darcy's law tells
Yes, sir.
us? Yeah, Darcy's law tells us that Q is equal to KIA or V is equal
V is
to
proportional to
KI. Now what is this V?
Ki.
What is this
Yes,
V?
sir.
What is this V? Is it the actual velocity or it is the
Discharge
average?
velocity.
Huh? Is it the actual velocity?
Basically, it is the discharge velocity.
It is discharge
No,
velocity,
sir.
that is fine,
Actual
but it is the
velocity is
actual
somewhat
velocity through the pores?
greater.
No, right? But why you are using this? Because it
No, sir.
gives, yeah, it gives you, Darcy's law has certain assumptions. What are those assumptions? Darcy's law is not
Maybe
always
the
valid. There are
flow should be linear.
flow should be
Flow should be linear. Laminar. Sorry.
Yeah, laminar, fine.
Darcy's law assume flow through all parts, cross section all parts, but actually flow through
And
one for porous part.
Yeah, so see this porous part,
porous part.
this
Yeah.
pipe, this entire, the flow will take place to the entire surface area. Now, had it been not given in the question that it is constant, then whatever you are trying, we could have taken that part. Okay, and for that we need some additional details. For example, the porosity values should have been known to us, because from this particular thing, this Darcy's expression, when you want to find the actual velocity to the pores, you need the porosity eta. Okay, but since this
Okay, sir.
velocity of
Okay.
exit is constant, so we can safely assume, means I am not telling that it is exact. Okay, these are all means whatever we are doing in engineering, these are all approximate things, but to a reasonable degree of accuracy. Is it clear?
Yes, sir.
Yeah. Okay. So now if you cut this pipe, what you will get? You will basically get a rectangle such that this particular dimension is L, and this dimension will be the circumference of this thing. Okay, the circumference of this pipe cross section. So circumference is 2 pi r or pi d. So what is the area of this rectangle? Pi d into L, means this is the total effective area through which the leakage is taking place at a constant rate. So that's why the velocity of emission is the emission discharge divided by the area through which the emission or the leakage is taking place. So as I told you, please look at the procedure carefully. There is no need to jump into means there might be some errors in this calculation, so that you can check from your side. But the procedure, you have to follow the procedures. Okay. Now the last problem. Okay, the last problem. Uh, what force components Fx and Fy are required to hold the black box stationary? Assume no mass to be accumulated inside the black box, means there's basically a box. Okay, there is basically a box. Okay, and at the different faces, the inlet or the outlet values for water and the velocity is given. Okay, so this is basically the control volume. Okay, the coordinate axis. Now what force components Fx and Fy are required to hold the black box stationary? Okay, now because of this fluid, okay, so because of the there are different inlets and outlets. See here, there is an inlet of water 20 liters per second, then here there is outflow 20 liters per second, inflow 31 liters per second, outflow, okay, Q2. Now Q2 is not given here, you can see, but Q2 is written and there is a outflow. Now you need to compute the forces Fs and Fy such that because of these inflows and outflows, the box is not moving. Okay, for the box to remain stationary, what is the forces? Now see, because of this water in rushing inside or water moving out, there will definitely be some forces exerted by the liquid on the sides or the walls of the box. Okay, the flowing water will exert some forces on the walls of this box. Okay, now you need to apply forces equal and opposite to the magnitude of this Fy and Fx. So basically the forces Fx, if suppose water is exerting force Fx and Fy, okay, on the walls of the box, then the box will start, the box will not remain stationary. Now in order to make or keep the box stationary, you need to apply opposite forces Fy and Fx, okay, of the same magnitude but the direction in the opposite sense, that is from Newton's third law, to keep the box stationary. Okay, so here which conservation principle will you apply? Momentum principle. Okay, yeah. So since not much time is left, I'll just discuss the solution procedure. See here, Q2 is not given, but it is given that no mass is accumulated. Since no mass is accumulated, the effective summation of all the discharges. Now see, Q2 plus Q4, okay, Q2 plus Q4 means the outflows are considered as positive and the inflows are considered as negative. So you can since there is no mass accumulated within the box, outflows are equal to inflow. So from here you can find Q2. Okay, so Q2 plus Q4 minus Q1 minus Q2 plus Q4 minus Q1 minus Q3 equal to 0. So apart from Q2, all the discharges are known. So Q2 is basically 23 liters per second. Okay. Now you apply momentum principle. So along x direction, you can see that all the velocities are given. Okay. Now here the velocities are making an angle, say 60 degree, here it is 40 degree. So you have to take the components along x and y direction. So you take the components along x and y direction. Okay. So for fx, rho q2 for example, rho q2. So rho q2 is this is 60 degree. So what will be the x component? What will be the x component? This is velocity, right? So if this is velocity, what is the x component of velocity? Along this direction, and this will be the y component. So if this is 60,
Cos 60.
this is 60, then the complementary angle will be 30 degree, right?
Yes.
So V component of V2 along the x direction will be V2, which is 40. So 40 into cos 30. So rho q into velocity is basically the force. So similarly, you take the components, you find fx, you find fy. So these values are basically, now what will be the component of V1 along x direction?
0.
0. There will be no component. So other than V1, this will have a component, V4 will have a component, V2 will have a component, V3 will have a component. Okay. So Q2, Q4, Q3. Similarly, for y direction, all the 4 velocity directions will have component. Okay. So you find fx and you find fy and you simply reverse the directions. Okay. So basically it has been asked to find the forces and force components. So you can like calculate these magnitudes, and that will do, and if required you can find the angle also, and you can find the resultant forces, but that is not required because in the question it is asked that you have to find fx and fy separately. Okay. So is the procedure clear? See, these are
Yes,
all,
sir.
yeah, these are all very simple problems, but you need to know carefully that which conservation equations you need to apply, and you need to carefully take the components, and you need to solve the problem. So it will require some more practice on your part, and I hope you'll be able to solve the problems. Okay. Okay, so it's ready time. Let's stop here. Thank you.
Thank you, sir.
Thank you, sir.
Yeah. Yeah, you guys can leave the meeting. Thank you.